The question that I have is, could you do a 1D consolidation example? Let's do an example. We have a 6-meter thick clay layer sandwiched between two sand layers. The water table is at the ground level. It is given that a footing loading has increased the vertical stress at point A by 150 kilopascal. Question is to find the pore pressure at this point 2 years after the construction of the footing. It is understood that there was hydrostatic pore pressure at point A before the construction of the footing, right? So the footing has produced an excess pore water pressure. So we need to find these two components, add them up to find the pore pressure at point A at the present time. It's pretty easy to calculate the pore water pressure before the construction of the footing. There is 10 meters of water above point A, and therefore the pore pressure equals 10 times 9.81, which is 98.1 kilopascal. Now we calculate the excess pore pressure. First we calculate the time factor, which is obviously given by this equation right here. C sub V is given as 2.5 meters squared per year, and then time, little t, is 2 years. H, which is half the thickness of the layer, because this layer is a doubly drained layer. So half the thickness is 3 meters, so 3 squared. So time factor is calculated to be 0.555. And then we calculate the dimensionless depth. We are interested in at this point right here. So the depth of that point is 1 meter. So we divide 1 by 3, which is again half the thickness of the layer. We get 0.333. Now I go back to this chart that we talked about earlier that gives you the value of local degree of consolidation. And I locate the point based on my values of the dimensionless depth and the time factor, which is 0.55, which kind of falls between these two isochrones. I get a value of 0.84 for the local degree of consolidation. Now you use the definition of the local degree of consolidation in order to calculate the excess pore water pressure, which is calculated to be 24 kilopascal. You add the two, the hydrostatic pore pressure and the excess pore water pressure, in order to calculate the total pore water pressure at point A at the present time. So that is calculated to be 122.1 kilopascal. The second part of the question is to calculate the settlement of the midpoint of the footing 2 years after the application of the footing. We are told to assume that the increase in the vertical stress is constant throughout the clay layer. What that means is we can take the midpoint of the clay layer, which is point B, and perform the calculations. We are also given that the initial vertical effective stress at point B is 120 kilopascal. So what's our approach? Well, first we are going to calculate S infinity. Then we are going to calculate U average. From the two, we are going to calculate the settlement 2 years after the application of the footing loading. So what we want to do is to make a sketch in the E versus sigma V prime space, mark the initial and the final points so that you will know whether you have to use the normally consolidated line or the swelling line or both in order to calculate the change in void ratio. So in this problem, the pre-consolidation pressure is given as 270 kilopascal, whereas the initial stress is only 120, and therefore the soil is definitely an over-consolidated soil. So the initial point plots over here, but then it's just a coincidence that initial plus the change happens to coincide with the pre-consolidation pressure, and therefore the final point coincides with that point right there. So we simply have to use the swelling line in order to calculate the change in void ratio between 1 and 2. So I calculate a value of 0.0193 for the change in void ratio, and then I substitute that in this equation in order to calculate S infinity. S infinity is calculated to be 0.059 meters. Note that I'm using the total thickness of the clay layer in calculating S infinity. Now we need to calculate the average degree of consolidation. We've already calculated the time factor at 2 years, which was 0.555, right? So all we have to do is to utilize this curve in order to calculate the U average. And for 0.555, I get a value of 80% for that. We know that U average equals S over S infinity, so S then is 80% of S infinity, which works out to be 4.72 centimeters.